Having discussed why light is a wave, it's now time to tell you that it's also a particle. And there are two big pieces of evidence for the quantization of light. The first is the Blackbody spectrum. Now, the Blackbody spectrum is not the spectrum of something that is black, because that would be rather boring. Rather, it's a spectrum of something that is hot. So we can think about the sun. The sun is hot. It has a particular spectrum, and by spectrum I mean how much power we have at each frequency in the electromagnetic spectrum. And in the case of the sun, most of the radiation comes out in the infrared and the visible and the ultraviolet. What theory can we use to explain the color of the sun? What theory can we use to explain what frequencies it radiates? Well, we use something called the Blackbody spectrum, and to get the correct Blackbody spectrum, you have to assume that light is made of particles, that it is quantized. A second piece of evidence is the Photoelectric Effect. Now, this is about the way light removes electrons from the surface of, say, a metal. So you shine light on a metal, and sometimes electrons are spat off. But if the frequency of the light is too low, no electrons will be removed. If you increase the amplitude of the light as much as you like, it doesn't matter. It's the frequency of the light that determines whether electrons will be ejected or not. So something important about the way the frequency determines the energy of light. And in fact, the way to solve this problem, again, is to say that light must be a particle. So the particle nature of light, these two pieces of evidence, led to the formulation of quantum mechanics in the early 1900s. Since this time, there's plenty more evidence for the quantization of light. There's a whole field of research called quantum optics, which is actually what I do, where we investigate phenomena like entanglement and quantum teleportation, and this all relies on the quantization of light. Let's consider now the Blackbody spectrum in some more detail. So what we mean by Blackbody spectrum in its idealized form will be something like this. Imagine we've got a box, it's made of mirrors, so that any light inside this box gets bounced around by the mirrors in a perfect sort of way. We heat this box up and the box gets hot, it'll start radiating because the electrons are jiggling around making electromagnetic waves. And so the light inside this box will have some color because it'll have some amount of energy in all the different frequencies. To find out what's inside that box, we punch a little hole in it and measure the light coming out. So this is an ideal black body. It's called black because until you put the hole in it, there's no light coming out of it. So we think about one dimension of this box. What's going to be happening is it'll actually fill up with modes. Because there's mirrors here, the light will be reflected backwards and forwards, and so we start having modes of the electromagnetic spectrum. And the energy in each mode is proportional to the amplitude of the wave and the frequency squared of the wave. So the energy is proportional to the square of the frequency. The energy in a mode is proportional to the square of the mode of the frequency. And that's really important. And it turns out to be wrong, because if you take this and you now calculate the expected spectrum, you get something called the Rayleigh Jeans Law, and it goes up quadratically as a function of frequency. So what this means, I've plotted this for a temperature of 6,000 Kelvin, which is about the temperature of the sun. What it means is that for higher and higher frequencies, we expect more and more energy per unit frequency. Or in other words, the energy is infinite and gets higher and higher as you go to higher frequencies. And this was the situation in physics at the start of the 1900s. It was something of a crisis, because this model of radiation by a black body predicted an infinite amount of energy. It was called the Ultraviolet Catastrophe, because as you go to bluer frequencies, it becomes catastrophically worse. Everyone agreed this was not likely to be the case. So Max Planck solved this problem by quantizing light. He said, instead of having the energy in a mode proportional to the square of the frequency, the energy in the mode must be some integer n multiplied by h mu, where h is a constant, now known as Planck's constant, and mu is the frequency. So the energy in a mode now scales linearly with frequency, and the energy is then divided up into blocks. You have n, some integer number of these blocks of energy called h nu. The size of a block is h times the frequency, and n is the number of these blocks or number of quanta of energy. So the energy in each mode now is said to be quantized. If you do this, you get a much nicer curve that agrees beautifully with experiments. Now, Max Planck showed this to his colleagues at a conference on the 19th of August 1900. He had just derived this formula to fit experimental data. He had absolutely no idea what it meant physically. So he presented it to his colleagues, and went away for 6 weeks and thought about what it could possibly mean. And the concept he came up with was that light must be divided into these little blocks. So when he wrote down this formula, he wasn't saying, I'm going to quantize light and this is the consequence it has. Rather, he found this formula that fitted, and then he had to go away and figure out what it meant. It was quite an unusual back-to-front way of doing physics, but had enormous impact.